This is a circuit containing the basic pieces behind any electronic device nowadays. And in this video, I'll explain to you how these tiny pieces all come together, so you can use these tools to make circuits yourself. But not just that, you'll see how logic gates are made at a transistor level, the most important device of the 20th century, as well as understand the information flowing through them with binary numbers, the piece of information all computers, phones, microphones, cameras, cars and more use, including yours. This is an LED. It has two legs, a short one and a long one. To power it up, it has to be connected to a voltage source, such as a battery, where the short leg is connected to the negative side and the long leg connected to the positive side. Unfortunately, a 3-volt battery is usually too strong for an LED like this one, which typically use about 1.8 volt instead. To get around this, we can add something called a resistor. It uses some of the voltage so that the LED can use only 1.8 volt. And now for the final piece, I want to add a switch. This switch simply allows current to flow if it's on and doesn't when it's off. Let's now add the logic part of the circuit, which is handled by logic gates. Although in real life they come in many different shapes and sizes, I'll represent them using their schematic symbols. There are only a few common logic gates you'll see often in electronics. The simplest of these is probably the NOT gate, shown by this symbol. It simply flips the state of the switch. So if the switch is off, the LED is on, and if the switch is on, the LED is off. Before I move on, it's probably best if I add some notation. You see, as we continue, these circuits will slowly get more and more complicated, and it would be best if we create some simple system for keeping track of what we're doing. We can do this as follows. We give the input and the output names, such as A and B. A and B can only have two values, either 0 or 1. 1 corresponds to the case of letting electricity flow through, where 0 corresponds to not doing so. We can put the NOT gate information in a table like this. When A is 0, then B is 1. When A is 1, then B is 0. And finally, we have the equation form, where I can write B equals not A with this bar on top. With this new way of thinking about equations, it's much easier to describe what logic gates are doing. Let's talk about the next logic gate, which takes in two inputs, let's call them A and B, and has one output, let's call it C. The AND gate only turns 1 when both A and B are 1, and otherwise it's 0, which has this formula. The OR gate turns 1 if either A or B are 1, which has this formula. Now you might be confused and wonder when the actual computer magic is gonna start, but you actually already have a lot of the tools. You see, as an engineer, a common theme is to break problems apart into simpler problems, which you have the tools to deal with. These logic gates are the simplest tools to deal with problems containing inputs of zeros and ones and outputs of zeros and ones. For example, in our LED case, a few common inputs you'd find may be buttons, switches, joysticks and more. As outputs, you might see LEDs, LCD screens, buzzers and more. If you don't have access to any of these tools at the moment, you can use some common digital circuit simulators. I especially recommend Logisim Evolution because it's free. Let's think about how we build a lamp for a room based on a few inputs. One is just the on or off switch, and one is the light input, which is 0 when it's dark and 1 when it isn't. We want the lamp to be on either when it's dark or when we press the button. As you already heard, we probably need an OR gate here, but that's not all. We also want a 1 here when it's dark, so we can add a NOT gate. We can make a table once again and see our outputs. An OR gate and a NOT gate together would have this formula. And in our table, we can see when the lamp would be turned on. It's also important to understand where they actually come from. These are transistors. We have the PMOS transistor and the NMOS transistor. The physics behind how they work is complicated, so for now, let's focus on how to use them, which is pretty simple. For an NMOS transistor, you have a gate voltage here, which is a sort of input. This top side is called the drain and this bottom side is called the source. When the gate voltage is 0, no current can flow. When the gate voltage is 1, current can flow from the drain to the source. For a PMOS transistor, everything is simply switched. The drain is on the bottom and the source is on top. When the gate voltage is 0, current can flow from the source to the drain. When the gate voltage is 1, no current can flow. Let's make a NOT gate with input A and output Y. When making a logic gate using transistors, you have a high voltage, called VDD, and a ground, which is a voltage equal to 0, shown by these symbols. When A is 0, current should flow from VDD to Y, so we need a PMOS transistor here. When A is 1, we want current to flow from Y to ground, so we need an NMOS transistor here, meaning that this is the schematic for a NOT gate. As it turns out, NMOS transistors are really good at passing zeros, so they're always placed between the output and ground. PMOS transistors are really good at passing ones, so they are always placed between VDD and the output, meaning that this is the general form of a transistor circuit. Let's try to make something called a NAND gate. It's a NOT AND gate with this truth table. The output is 1 when either A or B are 0. So we can put these PMOS transistors like this. Then we should be connected to ground when both A and B are 0, so they should be placed in series like this. If we now try to make an AND gate, we'll actually find that it's impossible to do so directly. But we can make a NAND gate and put a NOT gate behind it. The NOTs cancel and we get a normal AND gate. Similarly, we can make a NOR gate, which is a NOT OR gate. Putting a NOT gate gives us a normal OR gate. With transistors and logic gates, you're already very far into figuring out how something like a computer works. But to really make sure you understand them, you need to know about the language of computers. As we've already seen, computers have these ones and zeros that can be used to store data in them. If you add more wires, we have more data. What I want to talk about now is how to encode numbers with just zeros and ones. To figure that out, let's first compare it to how we count in our normal decimal system. In this system, we start with everything 0, then we count up with the rightmost digit until we get to 9. When we're at 9, we increase the second to last digit and reset the rest. If we go to 99, we get the same pattern. We increase the third to last digit and reset the rest. We can copy the same system for counting in decimal and convert it to counting in zeros and ones, called binary. So we start with everything 0. We increase the last digit by 1, but now we're out of digits, so we increase the second to last digit and reset the rest. This is in 10. This is 1 0. 2 in decimal, but in binary it's 1 0. We can continue to 1 1. Now we're stuck again, and we increase the third to last digit and reset the rest to get 1 0 0. To make it clear which is binary and which is decimal, I will add the subscript 10 and the subscript 2 here. The 10 because in decimal we have 10 digits, and the binary we have 2 digits. Let's count up to 16. Now here comes the neat part. This system of encoding data in zeros and ones isn't unique to numbers. We could do the same thing with letters. We could just make up some pattern. For example, 0 is lowercase a, 1 is lowercase b, 1 0 is lowercase c, and so on. But people have already done this for us, with the American Standard Code for Information Interchange, or ASCII for short. In an ASCII table, you can see the correspondence between binary numbers and every letter of the English alphabet, including some special computer characters you can see at the start. So for example, 65 is uppercase A, 66 is uppercase B, 8 is the backspace key. But even ASCII right now is a bit outdated. People have created the Unicode standard. There are 3 common encodings of Unicode. UTF-8, which uses 8 binary digits, or bits for short, to store a character. UTF-16, which uses 16 bits to store a character. And UTF-32, which uses 32 bits to store a character. So for example, this face with tears emoji is this number right here. Why stop at characters? We can talk about color as well. There are several ways to do this, but the most common is the RGB system, where the amount of red in a pixel is the number between 0 and 255, which means that it's 8 bits wide. Likewise, green and blue are 8 bits as well, so the color is a 24-bit number, where the first 8 indicate how much red in the pixel, the next 8 how much green, and the rest how much blue. As you can see, it's kind of annoying to write out these big numbers, so we like to break them up. Instead of looking at them in binary, we can look at them in something called hexadecimal, which goes as follows. Hexadecimal is counting with 16 different digits. Because we only have 10, we'll make up 6 extra ones, with the letters A, B, C, D, E, and F. So we start at 0, we count up to 9, the next digit is A, meaning that A is the number 10, then B is the number 11, C is the number 12, and so on, until 15 at F. Then after this we get 10 again. Remember, this isn't the usual 10, this is 16 in decimal. Why did we choose hexadecimal with 16 different digits? Because 2 to the power 4 is 16, meaning that 4 bits is equal to its hexadecimal digit. So if we have this number for a color of a pixel, we can turn each group of 4 bits into its hexadecimal digit to find the whole hexadecimal value. With this new notation, we can write numbers like these much faster. So those are the basics of logic gates, transistors, and binary numbers. But you can go further. If you click on this next video, you can go deeper into how all of this works.